All right, so I left you in suspense in the last video, but we're going to wrap up the rest of this section here. So let's take a look at this example. We have, we're being asked to determine if the function has an inverse, and if so, find it. So now you don't have to verify that it's a function, but if you wanted to, you could. So remember, the major condition that we're looking for, if it's a function, is as long as each x value only maps to a single y value. We can't have an x value mapped to more than one y value. So, so 3 maps to 0, 2 maps to 5, 4 maps to 6, 7 maps to 5. So it looks like we're good. None of the x values are repeated, so we should be fine. Now, if it's 1 to 1, remember, if we have a y value, it should always map to one x value. So let's see if that's happening. So we have a y value of 0. It's being mapped back to one x value. So 0 is being mapped to 3. 5 is being mapped back to 2. 6 is being mapped back to 4. And then 5 is being mapped back to 7. So this y value of 5 is being mapped to 7 and to 2. And that's a no-no. It only can be mapped back to one value of x. So there's the problem. So we do not have the ability to get an inverse here. So no inverse possible, and because it's not 1 to 1. So nice easy problem, but you got to recognize that that y value can't be repeated. It can be repeated in the one direction, so more than one x value can map to the same y value, and that doesn't hurt being a function, but it does hurt being having an inverse function. So, all right, so let's see if we can try to boil that down a little bit easier. And if we take a look at our next test here, we have the horizontal line test for inverse functions, which says a function f has an inverse function if and only if no horizontal line intersects the graph of f at more than one point. So this is a nice, easy test to verify that your function has an inverse or not. And if you'll notice, we already did these examples previously, and we did it algebraically, but let's just confirm that it's true graphically. So we have g of x equals x over 8, which we know is the same as 1/8 x. So we just have a line, and it's got a slope of 1/8, and we know it passes through the origin. So it's going to look something like this. And again, it doesn't have to be a perfect sketch, but we know that if we go over 8, we go up 1. So, and we can see that our horizontal line will always pass through it and only hit it at one spot. So this is 1, 2, 1. All right, what about this one here? So again, a square root is a little bit more complicated, but the big thing is where is that starting point? And we could always find that starting point if we look at where x is equal to 0. So if we solve this equal to 0, we can quickly show that x is equal to a -3/2. So that's the starting point. And so now we can just kind of shift it, or just kind of hook it from there, since it's not shifted up or down at all. So if we looked at -3/2, and again, it doesn't have to be perfect, it's just a rough sketch, but it still passes that horizontal line test. So we can see it only hits it in one spot everywhere. So this is 1 to 1. And then our final one is our parabola, which we already know fails, but obviously if we drew it, it would look something like this. Again, doesn't have to be perfect, but it fails. So that's no good. So is not 1 to 1. And I'm in the way. So, but that's, again, it's just a nice way to check it. So graphically and algebraically, we can check for one-to-oneness. And now the final process that we're going to look at in here is actually finding inverse function. What process can we follow to actually get that inverse function and create it? So now they walk through the steps on page 88 in your textbook. So if you go to your ebook and you can take a look at that and read through that, but it's actually very quick to show you it. So I'm just going to show you the process. So we have two examples here. So 5x plus 1 is equal to our function. Now, if we just follow this, as best you can, first step is just to change f into y, just to make it easier for us. So that's step 1. Step 2 is to actually interchange those variables. Because remember, that's kind of what we did from the beginning when we were defining inverses. We swapped those ordered pairs, the coordinates of those ordered pairs around, and that's essentially what we're doing here. So if we swap, that's step 2. Now comes the algebraic part. We need to solve this for y and get y by itself, and we could do this pretty quickly. So if we subtract 1 from both sides, and if we divide by 5, and I'm going to flip the sides around. Now we could make it even more detailed than this. We can split it into 2 fractions. We can look at it from a equation of a line perspective if we wanted to, but it's not really that necessary. So this is step 3, is just solving it for y. And now you're basically done. Step 4 is just to replace y with f inverse. Now, the only thing we have to be a little bit careful about is the domain and range of your original function. If this has any restrictions on it, then we're going to need to employ some restrictions on our inverse as well. But looking at our original function, is there any restrictions on the domain and range? No, both of those are all real numbers. So we really don't need to worry about restricting our domain and range on our inverse function. Now, what happens when we do have to do that? Well, let's see. If we take a look at this one, which is the same as the one up above, we know that the domain is restricted because it can't be below that -3/2. So our domain is going to be from -3/2 to infinity. And what about our range? So we didn't see it, but let's go back up and cheat here. So we can see that the y values don't start until we get to 0, and then they extend all the way up to infinity. So this is going to be from 0 to infinity. So more than likely we're going to have some restrictions on our inverse, but let's get our inverse first. So step 1, remember, is to just replace. Step 2 is to swap. And step 3 is to solve. So, well, we got to get rid of that square root. So we're going to have to square both sides. And now it's pretty quick. We can lose the 3 from both sides. And then divide by 2. So we got y equals x squared minus 3 all over 2. And that was step 3. And then step 4 is to rewrite it with our inverse notation. So, what can you tell me about the domain and range of our inverse? Now, don't overthink this. Because remember, all we're doing is swapping the x's and y's, which swaps the domain and range. So we already have them up here, so we know what the domain and range should be for our inverse. And so we're just essentially swapping them. So the domain should be from 0 to infinity, and our range should be from -3/2 to infinity. And if you're not quite sure about that, well, let's draw a quick little sketch. So we know we have a parabola, so we normally have that, and we have a modification to it, and there's also a drop in it because of that. Minus 3 is technically at the end of the function. Now it's not necessarily 3. If we split it apart, it would be 3 halves. So it's actually shifted down 3 halves. So our parabola would normally be something like this. Now I'm not drawing the whole thing in because, remember, we're restricting it. So, so we already know that it's going down to 3 halves, negative 3 halves. So that's good. But our domain, remember, is from 0 to infinity. So we only want this right-hand side. So we don't even want any of this. And so now it satisfies the horizontal line test as well, because you can pass a line through it and it's only hitting the graph in one spot, and which is what we want. So we need to have those restrictions, otherwise it's not truly an inverse invertible function. So, all right, well that wraps up this section. A lot of layers to this one, so just be really careful with it. It can be easy in some cases, but tricky in others. So, but if you have any questions, let me know. All right, that wraps up this chapter. So new chapter in the next videos. So see you soon.